Power functions. These notes are the notes on power functions, and we're filling out the worksheet, the first side of it. Power functions are functions that have a particular format. They're written in the form of x to the n, where the base is a variable, and the exponent is a constant. So examples of power functions are familiar functions such as x squared, x to the 3/4, x to the -1, if we use the variable z, z to the 7th, root x, because that's a power function, it's the same as x to the 1/2, etc. Notice we can have transformations of power functions, such as y equals 4x to the 2/3. That's simply just a stretch, a vertical stretch, of the power function y equals x to the 2/3. In this worksheet, we're going to just focus on the parent power functions without any kind of transformation. But once you can graph the parent function, of course, then you can go ahead and do the transformed graph. So, what makes power functions easy to graph is that you can always predict the shape of the graph in the first quadrant just by looking at the exponent. So let's have a look at three cases. Let's look at the leftmost one. What would the graph in the first quadrant look like for y equals x to the n, where x to the n is less than 0? In other words, where x to the n, where n is negative. So we have a negative exponent. And to try and think about what that graph would look like in the first quadrant, let's think about a graph that you are familiar with. Let's take y equals x to the -1. There's your negative exponent. That's 1 over x. And you know what that graph looks like in the first quadrant. It looks like something like that. And so these graphs would look something like this in the first quadrant: x to the -3, x to the -2/3. Any negative exponent, whether it's fractional or an integer, will look like this graph, the graph of x to the -1, or 1 over x in the first quadrant. Let's have a think about what the graph where the exponent is between 0 and 1. Let's think of a graph you're familiar with. Well, you know what the graph of y equals x to the 1/2, otherwise known as root x. It looks like this in the first quadrant. It gets less steep as you go from left to right. And so a graph of x to the 3/4, x to the 1/3, those exponents are all between 0 and 1, and they look like root x in the first quadrant. And then the third case we look at is y equals x to the n, where n is bigger than 1, and a very familiar example is y equals x squared. The exponent's bigger than 1, and it looks like this in the first quadrant. It gets steeper as you go from left to right. And you will notice that actually we've covered everything except for where the exponent equals 1, because then we simply get y equals x, and that function is of course very familiar to you. It's just a straight line. So we leave that case out. Alright, and so that means that graphs that look like x cubed, x to the 5/3, and so on, as long as the exponent's bigger than 1 and obviously positive, it will look like the graph of y equals x squared in the first quadrant. Now, to get the rest of the graph, the first thing we need to consider is there any more to the graph? In other words, the domain. Does the graph exist for x is less than 0? If it doesn't, then we're done. If the graph does exist for x less than 0, then to get the rest of the graph, we just need to establish whether or not the function is even or odd. And a quick review here of what an even or odd function is probably appropriate. An even function means that the output for negative x is exactly the same as the output for x. And such a graph has got symmetry about the y-axis. So if we know one half of the graph, we can draw the other half. So symmetry about the y-axis. An odd function is one that the output for negative x is the negative of the output for x, and such a graph we say has symmetry about the origin, which is a little harder to visualize in terms of symmetry about a point. What that means is you can think of it in two different ways. You have 180 degrees, one half of the graph. If you rotate it 180 degrees rotation about the origin, or you can think of it as a double reflection, a reflection in the x-axis, then y-axis, or vice versa. It doesn't matter the order in which you do the reflections. Okay, so reflect on one axis and then the other one. All right, so let's do an example. Let's have a look at the first example, example 1. We'll do a second example on the back. Sketch the graph of y equals x to the 2/3. Okay, let's check. Let's look at the exponent. It's between 0 and 1. So it's going to look like x to the half or root x in the first quadrant. There we go. So I know the first quadrant looks something like that. Now I'm going to ask myself the question, does the graph exist for when x is less than 0? When you do this, it often helps to write the function, and I use fn very often for function, in radical form. So what I've got is y is x to the 2/3 means the cube root of x squared, and I can do the squaring first and then the cube root, or vice versa. So I'm writing it now in radical form, and I've chosen to square first and take the cube root. Will there be an output when x is negative? Yep. Put a negative number in, square it, it's positive, and I can take the cube root of that for sure. I can take the cube root of anything, actually, positive or negative. So the answer to that is yes. There is more to the graph than just the first quadrant. If the answer were no, actually be very sweet, you'd be done. So to find the rest of the graph, I need to ask whether it is even or odd. So let me think. I know f of x, and notice when I ask this question, I'm now going to use f of x notation. So I change my notation to just make my life easier. I know that f of x is equal to the cube root of x squared. Therefore, f of negative x is the cube root. The input is now negative x. Note the parentheses, I have to use them. And I think about that. Okay, I'm plugging in negative x, square it, I get x squared. So that is actually equal to f of x. My graph is even, my function is even, which means I have what? Symmetry about the y-axis for even functions. So my final sketch looks like this. Here's the first quadrant, symmetry about the y-axis. There is my second quadrant. And I have a nice rough sketch of what the graph looks like. Turn over your paper and let's do a second example on the bottom of the page. So here at the bottom of the page, let's do an example 2. Okay, and let's do y equals x to the negative 3/5. Okay, oh, negative exponent, we know the first quadrant. So quadrant 1, it looks like x to the negative 1 or 1 over x. And so I know the first quadrant looks like that. Okay, will y exist when x is negative? Okay, to do this, let's rewrite the equation. And in fact, my equation, remember, a negative exponent means 1 over. So this is 1 over x to the 3/5, which is 1 over the 5th root of x cubed. And now I ask my question, if x is negative, what happens? Well, when x is negative, cube it, it becomes it's still negative. But can I take the 5th root of a negative quantity? Yes. Okay, you can't take an even root, but a 5th root of a negative quantity, no problem. So the answer is yes, there's more to the graph. Now I need to decide if it is even or odd. Remember, for this, it is now useful to use f of x notation. All right, I know f of x equals 1 over the 5th root of x cubed. What's my output when x is negative x? So I'm going to replace with parentheses x by negative x. And I think what happens here, all right, I cube negative x, I get a negative quantity, and then I take the 5th root of that, so I'm going to get a negative quantity out of this, and so I'm going to get the negative of what I'd get if x were positive. So it is the negative of f of x. So my graph is, my function is odd. And so to get the rest of my graph, I reflect first on one axis and then the other axis. So suppose I reflect in this, and then here is the other half of my graph, and that's what my final graph is going to look like.